Hi, I'm Arnie, and during this week's lab session, we investigated how a simple electric motor works using a battery, magnet, screw, and wire. An electric motor converts electrical energy into mechanical energy through the interaction between electric current and magnetic fields. In this experiment, we built a simple homopolar motor to observe how electromagnetism can produce continuous rotational motion. The aim of this experiment was to construct the motor, estimate its rotational speed in hertz, investigate how magnet orientation affects rotation, and observe what happens when the magnet is removed from the system. The apparatus used included one AA battery, a neodymium magnet, a metal screw, and a conducting wire. The magnet was attached to the end of the battery while the screw was suspended below the magnet. The wire completed the circuit by touching both the positive terminal of the battery and the side of the magnet. A slow-motion camera recording was used to estimate the rotational speed of the motor by counting revolutions per second. A label diagram of the setup was also drawn to show the arrangement of the components. To conduct the experiment, the magnet was first connected to the bottom of the battery and the screw was attached beneath the magnet. The wire was then positioned so that it simultaneously touched the top of the battery and the side of the magnet, allowing electric current to flow through the circuit. Once the circuit was completed, the screw and magnet assembly began rotating rapidly. The rotational speed was estimated using slow motion footage. The number of revolutions completed in 1 second was counted manually. This process was repeated 3 times under slightly different conditions, and the values were averaged to improve reliability and reduce random error. The average rotational speed of the motor was approximately 16 Hz, meaning the motor completed about 16 full revolutions every second. The experiment was then repeated with the magnet flipped to investigate the effect of reversing the magnetic field. When the magnet was flipped, the direction of rotation reversed. This occurred because reversing the magnet field also reversed the direction of the magnetic force acting on the current-carrying conductor. According to Fleming's left-hand rule, changing the direction of the magnetic field changes the direction of the force, causing the motor to spin the opposite way. The magnet was then disconnected from the battery. Once removed, the motor stopped immediately because there was no magnetic field interacting with the electric current. Without this interaction, no magnetic force was produced, so rotational motion could not occur. This demonstrated that both electric current and a magnetic field are required for the motor to operate. The behavior of the motor can be explained using the motor effect, where a current-carrying conductor placed in a magnetic field experiences a force. This force can be described using the equation F equals BLI sine theta, where F is the magnetic force, B is the magnetic field strength, I is the electric current, L is the conductor length within the magnetic field, and theta is the angle between the current and magnetic field. In this experiment, the current flowing through the wire interacted with the magnetic field produced by the neodymium magnet, generating a tangential force that caused circular motion. The experiment also demonstrated energy conversion. Chemical energy stored in the battery was converted into electrical energy, which was then transformed into kinetic energy as the motor rotated. Stronger current flow produced a greater magnetic force, increasing rotational speed. Several assumptions were made during the experiment. It was assumed that the battery provided a constant voltage and that the magnetic field remained approximately uniform. It was also assumed that air resistance and friction had minimal influence on the system. There were several sources of uncertainty throughout the experiment. One uncertainty was manually counting revolutions from the slow motion footage. Since the high rotational speed made precise counting difficult, another uncertainty came from inconsistent electrical contact between the wire and magnet, which occasionally interrupted current flow. Friction between the screw and magnet may also have slightly reduced the rotational speed. Additionally, changes in battery charge could have affected the amount of current flowing through the circuit. Despite these uncertainties, the results were consistent across all three trials and clearly demonstrated that the principle of electromagnetism and the motor effect was true. Overall, the experiment successfully showed how electric current and magnetic fields interact to produce rotational motion, forming the operating principles behind electric motors used in everyday devices.